Okay, today I just gonna quickly go through the checkpoint utils in PyTorch. So it's essentially just a utility tool to cut down the activation memory that is saved in your GPU while you're actually training a model. Um, it can it can actually take up a lot of space as shown here in Llama 2, 13 billion of float point 32 model with 16,000 context token, and it actually took up a lot of space, a lot of CUDA memory in your during your training process. So it's about this size, and with checkpointing, provided you are using the full checkpoint, you can actually cut down this into nearly zero. So for the record, this post on Medium by PyTorch is basically what we're trying to follow here, but we will extend into the actual implementation in PyTorch codebase. So yeah, thanks for this post. It helps a lot. So if you're trying to really see how checkpointing is doing its work, here I have a simple model with which has a really big hidden state that is supposed to take a lot of space in activation. So here we use checkpointing this skill. We can actually see that before the all of this model initialization parameters, all that kind of stuff, before the forward pass we have this size, and after the forward we increased a little bit of memory, and after the backward it is a lot of activations and all that kind of stuff were released, and it saves a lot of space. So far so good. But without checkpointing, as you can see here, it is actually very, very wait, I think this might be flawed. Yeah, this makes more sense. Yeah, so again, without checkpointing, as you can see, before the forward pass we have this, and after the forward pass, as we are saving our activation for the backward pass, we have a lot of GPU memories that is being taken place by the activation. This is far exceeding the the scope of our memory parameters and gradients and all that kind of stuff. But with this activation trick, that for the same model we're only max out at 26. So yeah, very effective. So let's go back to this post. How we're actually doing this, we rely on this this hook that is officially supported by PyTorch, that is going to raise our custom function before and after every activation tensors were saved. As here is a super a simplified version of it, and we have a tensor, and with this hook we call any function, right? And while we're actually squaring this x, we will save this tensor itself, right? Because the derivative of the square is 2 multiplied by the tensor itself, right? So we store this x, but inside our custom this hook function, we actually append this x into our custom storage and return this index of this x rather than the tensor itself. So it's like an index. And while we're while we're at it, we can safely go downstream to the other layers of network, whatever the following model is. So far so good. And we call backward. And when the gradients come back into our square, it will actually trying to take out this saved tensor. Hence, this unpack hook was called. And it will actually use this packed, the return of this pack function as the input, and it find out the actual saved tensor, which is the x from the storage. And we have our correctly calculated tensor here, gradients here. So this implementation actually does not save place of any kind. It just move this x into another place. For the record, you can actually if provided that no hooks were defined, you can actually think of something like this. It for the default behavior, it just return x, and when you unpack it just return x. Okay, but here we actually just move it to another place, and we find this thing with the index. So this is a preview of our final implementation, where we actually throw away this activation to cheat the autograph engine that we already saved our intermediate activation for the later backward pass, but we actually didn't save it, and we will recalculate it when we backward when we were back propagating all the things. So this is like a more complex version of the previous one. Also, the way we actually use this, I'm sorry, I will have to go back, is we just wrap our custom module of whatever kind, wrap this with the checkpoint utility, and followed by a lambda function that will actually return the input of this module. Here it's just an x, right? So same here. If we call our checkpoint function, this is the function. This is the actual module we're trying to checkpoint its activation, and this is the input for this function, similar to here, to the actual implementation here. And inside, when we call the forward on this function, it will execute this actual module with this context, right? So this is the most important thing, the checkpoint hook, like the one we just talked about before. When we're running the forward pass, we're trying to inside this function, we're trying to save the tensor of any kind, the activation. It will call this pack function, pack hook, that actually saves nothing. This is the unused x. Here is the tensor we're trying to save, but it's just unused. It's thrown away. It's never saved for any reason. We just increment this tensor count by 1. And this frame is like some kind of a central command or like a storage place for all this checkpointing strategy. It's just a list and a counter, right? So far so good. And the forward pass is complete, and we call backward on this. And the backward pass also will, call call this unpack hook, right? And when the first, like, imagine like, here's your checkpointed module, right? When you are forward, you go from the top to the bottom, right? Layer by layer. And when you are backward, back propagating all this, you goes from the bottom to the top, right? So this logic, the checkpoint recomputation thing, only happens once. Only happens when you're at the bottommost, the last layer of your module, which is the first module to be recompute, the first module to whose gradient have to be computed with. It will only be recomputed once. Right. Here, with this recomputation hook, we call the same function, the same forward function. But this time, with the same kind of strategy, this save tensor hooks, this time, while we're running our forward pass, we saved our every tensor we're trying to save. Here we actually save it, but to the frame. Remember, we are talking about the frame is actually the whole command center of all this checkpoint strategy, right? This recomputation logic save this new tensor to its core command center. So after this forward pass is finished, we have our new, fresh, calculated activation here, which we can actually retrieve it with the index. So this might be a little bit of, tricky to understand, because it's like two different forward paths. The first is like the regular forward pass you are seeing, for the whole model, right? It just flows from the bottom flows from the top to the bottom, only recording the activation, the index of the activation. The second forward pass is when we're trying to backward from the bottom, right? Here it reruns this module, this specific module. And as the module itself didn't change, it's the same function, the sequence of the saved tensor didn't alter at all, right? So for example, if there's like 5 tensors, 1, 2, 3, 4, 5, and it's in this sequence, and they were thrown away, we recomputate with the exact index, and thus can be retrieved with the same index. This can be kind of tricky. I don't see. This might be a good place for you to pause for a little bit, and if you're not familiar with all this kind of stuff, I believe you could really go back to the AutoGrad engine and figure all this kind of stuff out. All right, so this is also a simplified version of it. It's time to jump into the actual implementation of this. So for this checkpoint hook, it's actually like this. So the same here, we have our checkpointed function, which should be a module PyTorch module and our args, which should be passed into this function. And we only focus on the non-reentrant version of this implementation, which is more modern and more decoupled and more stabilized, which makes no edit to the compute graph. Anyway, so here it is more like complex implementation. It uses this generator and all this context function and all that kind of stuff. But anyway, first, when we're in this function, we have to save the context, like all and like the state of our computation, all that kind of thing. You know, you don't want to like recomputation with a different kind of randomized seed when you are trying to checkpoint a module that was with randomness, like drop out and like things like that. So we're trying to save our like random states and all that kind of stuff in this generator. So the first yield, which is here, it stops into this place before we go into this checkpoint hook, right? So we saved our RNG state, randomized state, and we knew our checkpoint frame, exactly what we talked about before. And with this hack, we'll come back to this later, but just remind this, like this is just solely for like storing our inputs for the module. It just saves the tensor, but not in the way we like we would like it to be saved in this simplified implementation, because it suck. It will like, it's a compute graph thing anyway, right? So when we first run this generator, it stops here, and it runs this forward pass, right? This is the first run of our generator, and this forward pass is here, and this forward pass will be wrapped under this hook, right? So it's not like how you see things like here, it's you know, line by line, you know, arranged perfectly. It's not like this. It's, you know, wrapped in this generator thing. You will stop at this, but the hook, you know, the context into the context function is executed, and the actual forward thing is actually executing under this context, right? So go back to this recomputate. Should come back to this hook, right? So this is similar to what we've seen here, the checkpoint hook. It's basically do the same thing, but with different methods and more case thing, you know, edge case handling and other kind of stuff, right? So this holder is actually the exact reference to this counter. It's doing the same thing, but just differently. And So far so good. And when we run our backward pass, this unpack thing will be raised, and we will start our second forward pass to recompute all the tensors that were thrown away. Same here in the unpack hook, but different. What is different is we get our context from the this input saver, the hack we just talked about, and we took out our tensor from it, and we do the exact same thing, just like this recomputation hook. We recomputate all the activation, and we will save into our frame, right? We save our X to the target frame. Boom, we have our already recomputed tensor, and we take it out, and we got our fresh activation. So basically it's the same thing but with different implementation. So the most interesting thing here is definitely the noob the noob tensor, I guess. It is checkpoint hook. No, it's checkpoint function. It's the generator, yes. Yes. So this is the this is actually a autograph function. It allows you to have custom operations other than the previous defined operations on PyTorch. And the way you use it is like you define a autograph function here, and you call the same forward and backward thing, except you can actually save the intermediate activation using save for backward call. And the reason why we're using this is actually we want to fully utilize the autograph engine and all the computation graph sort of things, because you don't want to break the computation graph like the way we're doing here. Like if you're trying to just passing the index, it's no longer a tensor and it's bad kind of thing. So you actually wanted to implement this by a custom function. So here you get all the input, and you save them into this custom operation and its context. It's zipped into this one. It's like a dummy operation where you can actually pack this package, which is the tensor you want, into this autograph operation, and you can get it out using the getArgs keyword. So it's super smart. Right. So basically that's how the checkpoint thing work here. I think it's really nice for us to really get to know how the action, the thing work under the hood, because there's a lot of, thing you can actually customize, because you can, for example, you can have your own context function here where you can actually execute some of your like custom function before and after the checkpoint. So yeah, that's how the whole thing work here, and we'll call it a day. Yes.